Hello everybody, I am Dr. S.S. Patil. So I will be giving a expert talk on introduction to design of reinforced concrete beams. The learning outcomes of today's talk. At the end of this session, the viewers will be able to understand the basic concepts in analysis and design of reinforced cement concrete beams. Introduction. Reinforced concrete beam is a structural element which is subjected to lateral loading. Due to lateral loading, the cross section of the beam is subjected to bending moment and shear force. Since it is subjected to a bending moment, it is termed as flexural member. The following are the assumptions for the analysis and design of beam as per IS 456-2000. The plane section normal to the axis remains plane after bending. So this is a general assumption which we make in theory of simple bending. The maximum strain in concrete at the outermost compression fiber is given as 0.0035 in bending. So this is maximum strain allowed in concrete. The important assumption is the tensile strength of concrete is ignored. Concrete is very weak in tension, therefore its strength is totally ignored. It is not at all considered for analysis and design. So the next is the stress in reinforcement is derived from respective stress strain curve for the different types of steels used. It may be it may be a mild steel, it may be Fe415, it may be Fe500. Typical curves are shown in figure number 1 in the next slide. The design. So this is figure number 1. So this will give you for HYSD bars. So this is idealized curve for stress strain curve for steel, and this is normal stress strain curve. Then for the design purpose, the partial safety factor assumed for steel is 1.15 and for concrete is 1.5. The maximum strain in tension in the reinforcement in the section at failure shall not be less than, or the steel should yield. So that's why stress in steel divided by 1.15 ES. So this is your partial safety factor for material plus 0.002. So where Fy is characteristic strength of steel and Es is modulus of elasticity of steel. So this is stress strain curve for steel. Now we get different types of RCC sections. Either it may be a balanced section, it may be a under reinforced section, or it may be a over reinforced section. A balanced section is one in which the strain in concrete, the ultimate strain in concrete and steel are achieved simultaneously. That means the strain in concrete is 0.0035 and strain in steel it is Fy upon 1.15 ES plus 0.002. So both are achieved simultaneously. So that section is called as balance section. This is a strain diagram for balance section. And next one is under reinforced section. So under reinforced section is one in which the strain in steel is greater than, or the steel will yield. The strain in steel is greater than Fy upon 1.15 ES plus 0.002. So therefore strain will yield. So due to yielding of this particular steel, there is a ductile failure of the RCC section. And the strain in concrete, it is less than 0.0035. That means concrete has not yet yielded. So therefore this particular section, it is called under reinforced section. Here steel will fail first, due to which the member will have a ductile failure. It will give us a sufficient sign before failure. Then the last one is over-reinforced section. In case of over-reinforced section, steel provided is more. As you see here below, steel provided is more. So therefore what happens? Steel doesn't yield, whereas the concrete will yield. That means strain in concrete is greater than 0.0035, whereas the strain in steel is lesser than the yield value. So therefore here concrete yields first. Since concrete is a brittle material, the failure of the beam will be brittle in nature. There is a sudden failure. So therefore the IS 456 allows design of only balanced or under-reinforced sections. Since the steel reaches its ultimate value first, the failure of the beam is ductile. So it gives a sufficient sign before failure. IS 456-2000 does not allow the design of over-reinforced section because the failure of over-reinforced section is brittle in nature, hence it is sudden. So that's why the sudden failure is not to be allowed. So the next is the limiting values of the depth of neutral axis. Based on the different types of steel, for mild steel it is 0.53 axiomax by D, and for Fe415 it is 0.48, then for Fe500 it is 0.46. Now this will give us a stress strain diagram of a singly reinforced RCC beam. Singly reinforced means reinforcement is there on only one side, that is a tension phase. Now here you will find, here XU is the depth of neutral axis. XU is the depth of neutral axis, and here you get the strain, maximum strain, it is 0.0035. Maximum strain allowed is 0.0035. And if you see the stress block parameters, that means, so since the concrete in tension zone is totally ignored, you will not find any stress diagram in the below neutral axis. So entire tension is taken by steel. So entire tension is taken by steel. So therefore below neutral axis you will not get any diagram for stress. It is directly at the steel level you will find T, that is 0.87 Fy into EST. And for the concrete you are having the extreme fiber is having a stress of 0.446 FCK, where FCK is characteristic strength of concrete. And in limit state method we consider a up to 3/7 XU, it is the rectangular stress variation, and in the rest of 4/7 XU it is parabolic. So therefore if we find out the CG of this particular rectangle and parabolic portion, we get it at 0.42 XU. So the CG of this, it is at 0.42 XU from extreme fiber. So that is required to calculate lever arm. So lever arm is, for equilibrium, C must be equal to T. What is C? C is area of this stress diagram into breadth. It is 0.36 FCK XU into B, that is your compression C, and that must be equal to tension T, that is 0.87 Fy into EST. So for C equal to T, so for finding the moment of resistance, it is either T into lever arm or it is C into lever arm. So if I take C into lever arm, it is 0.36 FCK XU into B multiplied by lever arm is D minus 0.42 XU. So this way we can analyze and design the RCC sections. Thank you one and all.